We are discussing about semantic segmentation using deep neural architecture, and in the last lecture I have referred to a very popular segmentation architecture which is called U-Net architecture. So, in this lecture I will give a brief overview of that architecture. So, in U-Net architecture the computation is carried out in two successive stages. Like the previous architecture of semantic segmentation, there is a path for downsampling and upsampling. Here also you have the path for downsampling and upsampling. We call it as a contracting path and also an expansive path. So, in the contractive path we have repeated application of two 3x3 convolutions, each of them is followed by a rectified linear unit and then a 2x2 max pooling operation with stride 2. And at each downsampling we also double the number of feature channels. That is how this architecture is specified. You can get the details of this architecture by the paper what is shown here, and you can get it from the internet. About the expansive path, as I was mentioning, that it is a repeated upsampling what is used for the feature map, and there is a 2x2 convolution or upconvolution is used, and in the contractive path where the number of channels were doubled at every downsampling, in upsampling, that means in the expansive path rather the feature channels are getting halved, and a concatenation also is there from the contractive paths output. We will show in the diagram. So, in the expansive path we are using the upsampled features and also the features what is being computed in the contractive path, those are concatenated. So, half of them are coming from there, and then using them you are basically passing it to the next stage. So, it has two 3x3 convolutions after doing upsampling, and it goes through the stages. Finally, the size of the image output becomes the same as the size of the input, and you require cropping to keep this constraint of size. And at the final layer, when you have generated all these pixels at the output, then for each pixel you classify those pixels into a number of classes. So, every pixel at the final layer it is represented by a feature of 64 dimensional feature vector, and those 64 dimensional feature vectors becomes the input to every classifier. So, in total there are 23 convolutional layers, and in particular this work it is applied for medical image segmentation or segmentation of microscopic images, and there are data augmentations which are used to increase the data pool. For example, they have used simulated deformations on training images. So, this is a schematic diagram which is taken from that paper itself. It is a U-Net architecture, and you can see that how the contractive path it is downsampling images of different sizes, and the number of channels are getting doubled there, and then in the expansive path you have upsampling images, and not only that, as I was mentioning, there is a concatenation of features. So, these features it is concatenated at this stage. So, half of this is coming from this stage and half of them is coming here, and it becomes once again this becomes the input to the next two convolution layers. Then again it is upsampled and it is performed in the same fashion. So, this is the operation what is being done in the U-Net architecture, and you using the input output specification you train it, and then once the training is over, then you can use it for the purpose of semantic segmentation. So, some of the results which are there in that paper, I am just reproducing them. So, you can see that these are microscopic images. The top one is showing the segmentation of objects, that these are the cells, and there the yellow border is the manually segmented, that is the ground truth, and the color part is the result. So, it is very close, we can see the bottom rows and the pairs of images are shown, original image and also segmented image. It is quite interesting, and it is shown that it is very nicely it captures the corresponding segments, and which corroborates with the ground truth also very close to it. So, next another kind of architecture we will be discussing and we will be considering another types of problems which could be solved using neural architecture. These networks are called recurrent neural networks. So, let us first understand difference between a recurrent neural networks. For example, the conventional neural network including CNN, there is no feedback. It has been shown in the left side that NN block, the green NN block, where the input is x and output is y, and there is no connections from the output to the towards input. Whereas in recurrent neural networks, you have a feedback, you have a connections from the output part to the input block. So, in the conventional neural network, it is a feed forward and there is no feedback, whereas in the recurrent neural networks, you have feedback from output of a neuron. Conventional neural network, it handles fixed size input and output. In the recurrent neural network, input could be of variable size. It is the sequences in the input, the output, or in the most general case both. Conventional neural network, it is a fixed number of layers, and since there is a feedback, actually it can simulate an infinite number of feed forward network. It can unfold into an infinite number of layers. So, this is the characteristics of recurrent neural networks. Some of the applications of recurrent neural networks, let us quickly visit some of those applications, like semantic labeling of a sequence. So, it can classify the input as a sequence, then prediction in a sequence. So, using previous video frames to inform the understanding of the present frame, one kind of example, or you can consider a language model. It tries to predict the next word based on the previous ones, and sequence translation and generation, where input is a sequence and output is also a sequence. So, the basic feature of the recurrent neural network is that it introduces cycles and a notion of time. So, consider this particular diagram, and here the red square is representing a recurrent neural network node. So, input at time t x t, and then there is output y t, but the intermediate output from the network, which has been also given as a feedback. So, you can see that so input is not only x t, even the previous time instances output is also input to this block h t minus 1. So, as if there is a one step delay, and this is how it works. So, this is used to design to process sequences of data, and it can produce sequences of outputs. Because of this feature that you are introducing a notion of sequence or time, and it's kind of a delay in the processing. So, we can consider when you are giving input can come as a sequence, and when you are producing output will be also a sequence. So, to analyze a recurrent neural network, you have to unroll or unfold the neural network, and number of stages of unrolling, it depends upon the length of the input sequence. So, you consider this, that suppose you have 3 length of sequence is 3 x naught, x 1, x 2. So, x naught is the past. So, the difference you note when we consider so digital filter, as if the input is coming from the left side and it is being shifted towards right, but here the past is always shown at the in this figure in the top side, and all the present are following successively. So, as you proceed in the time domain, because it is unfolding over the time instances. So, your always the temporally present sample or current sample will be shown at the bottom, or at the layer which is successive layers, always the temporarily following inputs will be coming in the sequence. So, if there are, say for example, sequence length is 3, so you can consider there are 3 such unfolding. You can draw it also in this fashion. That means, you provide input x naught in the first stage, get output y naught. Also, it generates an intermediate output h naught, which could be equal to y naught or which could be some function of y naught. And that becomes the input to the next RNN, next stage, next block of neural block. It is unfolding, it is the same RNN is doing, but at that time instant it is operating with input x 1 and also from the intermediate input h naught, generates y 1. Next time stamp it will be input x 2, then h 1, both are input, that is intermediate output of the previous time instance is h 1 and it produces output y 2, also generates an intermediate output h 2. Since there is no other input and you may not observe, so maybe no, your sequence has been generated as y naught, y 1, I 2 from x naught, x 1, x 2. That is the kind of explanation of the working of RNN. So, the learning algorithm what we use, if I unfold this, the same backpropagation algorithm can be used. So, this is trying to elaborate that particular aspect, that relationship between the intermediate output and also the past input or present input and past intermediate output. So, you can see that y is function of h t and h t is function of h t minus 1 x t of that RNN block, where w is the parameter. So, h t minus 1 is the old state, x t is the input vector at some time stamp and w is the function with parameter w and h t is the new state. So, the same function and the same set of parameters are used at every time stamp, and y t can be considered as a function of h t, it is a linear function. There is a the w h y is the weights connecting the intermediate output of the neuron to the final output. So, one of the form of h t could be that it is tan hyperbolic function and it has been shown by this weight set. So, w h h is a matrix which is producing the vector h t minus 1, which is producing this particular form, and w x y h x t is another set of inputs. And relationship between y t and h t is, it is w h y h t, is the linear combinations from h t. So, one particular example is shown here. Say in this case, it is a example has been drawn from the language processing, natural language processing or string processing. So, what we are trying to predict? We are trying to predict the next character of a word. So, there are training sequences. So, one is say hello is a training sequence, and as you can see the this RNN input, it can unfold the RNN into this, since there are the length of the string is 5 and there are prediction is 4. So, we consider unfolding of RNN till 4th stages of input character, and this is how the input is proceeded with temporal timestamp, and this is the structure, and so these are the weights at this stage, and this is the weight for h t minus 1. It is an one dimensional input, it is shown here. Now, hidden layer has a three input, sorry, hidden layer has a 3 node, 3 vectors. So, accordingly you should have the weight vector w h h and also w x h x t, that should come here, and then you are using tan hyperbolic layer. So, there are 3 such nodes here, and from there your output, which is also considered as a output of vector, 4-dimensional vector. Now, you are using here hot encoding. So, you can see the encoding which is used here. So, for h we are using a 4-dimensional hot encoding here. So, this position 1 shows h, this is E, this is L, this is L, and your outputs which are being produced here, the specified ground truth should have been here, it should have been 0 1 0 0, but instead you are producing this output. So, the loss function will be determined in this fashion. Similarly, this is the production of L, I mean it should have been L, but it produces this output, and otherwise the ground truth should have been 0 0 1 0. So, in this way the loss functions are to be defined. These are some examples that what are possible configurations and how different kinds of neural networks could be used, different architectures could be used for solving different types of problem. Here you can see that we have given some numbers, and each rectangle is a vector and arrows represent functions, and input vectors are shown in red and output vectors are in blue. So, let me just explain. So, suppose these are different configurations. First one is 1-to-1 configuration, which means input is a fixed vector and output is also fixed size output. So, example is an image classification, and this is a conventional neural network processing. You do not require RNN for this kind of processing. Whereas, the second one, which means this particular structure, the input is a fixed size input, but output is a sequence. Now, here you require RNN, and so it is a sequence output. The example could be the image captioning, which takes an image and outputs a sentence of word. The third one is, so this is a sequence, output is fixed. So, typical example could be that, say, sentiment analysis, where a given sentence is classified as expressing positive or negative sentiment. Fourth applications, so this is the fourth one, where input is a sequence, also output is a sequence, and this is an example could be the machine translation. It reads a sentence in English and then outputs a sentence in French, for example, a typical example of a problem. Here also RNN should be used. So, only for the first one it is a conventional network. For all this kind of sequence processing, we need to use RNN. Consider the fifth one. You have this synchronous sequence, input output sequence, and it could be the video classification for labeling each frame of the video. So, these are some examples of RNN, use of RNN in different applications. Sometimes you can convert even a fixed size input as a sequence by following certain predetermined order of scanning the input data. So, we call it sequential processing of non-sequence data. For example, for image we can scan from left to right and top to bottom. Now, that itself will provide you some sequence of regions, blocks. Now, those could be input to an RNN and we can process it for various purposes. So, this is this is showing one kind of processing. So, the blocks are moving in a sequence and we would like to classify images by taking a series of glimpses. Another example also, classify images by taking series of glimpses. So, the application of this kind of one such very popular application is image captioning, where image regions are could be also scanned, but in this case what it does that it represents the image as a feature vector using a CNN, and that is input to the to an RNN, and the descriptions one by one, the descriptions of the output. Once again, the number of the length of the output sequence decides the length of the unfolding of RNN that has to be there. So, for example, in this particular figure, the image could be described as the straw hat, and that is a sentence. So, it has a start and it has an end. So, with that kind of specifications, you are training the RNN in this way. So, use a convolutional neural network to describe the feature and then followed by a recurrent neural network to extract the caption. So, it just shows the workflow that you use a convolutional neural network where image is an input and it goes through several layers of convolutional neural network, and finally, you represent it as a feature vector. In fact, the last layers of fully connected layers, they are mostly used for classification. You can remove that layer and you can use only the representation of the last layer of the fully connected FC40, that means the feature dimension is 4096 at the last layer in this case. So, that could be the input to your RNN, and also the input, another input is a start symbol from where you are starting the sentence reconstruction. It reconstructed the sample y naught, that itself is the input towards your intermediate sample. So, this is a sample and it goes like this. So, in the same way the way RNN operates, and then it can generate a sentence. So, as you train on a number of images, it depending upon the image content, it tries to predict those levels which are being trained in a network. There is a data set which is called Microsoft COCO, and it has say 120k images, and for each image there are 5 sentences, and used it for training. And this is an example. So, you provide this as a training set to the network, and then you can generate different kind of image captions. So, some examples are shown here. Consider the first row, top row, and the leftmost image, where you have the man in black shirt is playing guitar, and say other one is shown as construction worker in orange safety vest is working on road. So, these are very interesting results, and presently lot of work is going on video summarization, image captioning, and many other things using this kind of network. So, let me summarize the topics and whatever we have covered under this deep neural architecture and its applications. So, we have seen that deep architecture works in the same principle of artificial neural network, but it has a large number of hidden layers and it has a large number of weights. One very popular deep neural architecture is a convolutional neural network, because it can learn filter weights and it can share those weights, and there are 2 types of layers usually in this process. One is convolutional layer, another is pooling layers for the feature description, and there are 2 stages which are involved: feature extraction and classification. So, in the classification stage usually we used fully connected neural networks. So, there are variations of convolutional neural networks. Say ResNet, it processes residual errors. Then RCNN, it has a region proposal network and it localizes object, and also it could be fully connected CNN, where it uses image segmentation. And then there is recurrent neural network, where it is a different kinds of neural architecture. It is quite different from convolutional neural network, because it has a feedback loop. It is not a feed forward network, and recurrent neural networks are mainly used for processing a sequence. So, with this let me stop here, and this is the end of this particular topic and this lecture. Thank you very much for listening to my lecture.